In section 2.1, we're going to look at a bunch of matrix operations, including addition, multiplication, and then some more exotic things like the transpose later on. So first we're going to think about a couple different ways that we can denote an m by n matrix. One way we've seen a lot of is in terms of the columns of A. We can write A as a bunch of vectors, A1 to AN. Note that this is n columns. And then each of these vectors, A sub I, is an m vector. There are m entries here. Another way to say that is we say that this vector is in Rm. So we've seen that before. Another way that we've dealt with, we haven't given any notation to, is that we could denote this by the entries individually of A. So again, there are m rows, and there are n columns. And then each entry here refers to a specific part of that matrix. So A11 means that we have the first row and the first column. AMN is the mth row and the nth column. And then in general we have AIJ is the ith row and the jth column. And it's going to be useful to think about things in terms of the individual entries like this. Note that some special entries are the main diagonal entries. These are the ones of the form AII. So that is A11 and A22 and A33 and so on. If we have a square matrix, if m equals n, then this really is the main diagonal. If m does not equal n, then it's going to be a little bit cut off. So for instance, the main diagonal entries might be here if n is greater than m. Another important matrix we're going to look at is the zero matrix. Just like we had the zero vector, we can talk about the entire matrix being zero. That's going to be important. And then we have a bunch of pretty easy to show results from this theorem. So we're going to let A, B, and C be matrices of the same size. That's very important. And let R and S be scalars, numbers. If we have that, we have A plus B equals B plus A. Let's just look at that one a little bit. We have A plus B, so let's say we had 1, 2, 3, 4. And we added that to 5, 6, 7, 8. We've done this before, but we can just add those entries by each entry. So this would be 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8. And what we know from addition is that we could write this instead as 5 plus 1, because addition is commutative, 6 plus 2, 7 plus 3, and 8 plus 4. And then we could have written those matrices in the opposite order, B plus A. So really, this result just follows from the fact that you can reverse the order of addition in real numbers. And a lot of these results come from that same fact. A plus B plus C is A plus B plus C. Which two do you look at first? That's just from the real numbers. A plus 0 equals A. That's just adding 0 to any real number gets you that back. If you take a scalar times A plus B, you can distribute that scalar to each of those numbers. That's straight from real numbers. And the other two are as well. If you take two scalars and add them together, you can distribute the matrix through those scalars, and you have associativity of the scalars in multiplication. You can check all of those, and all those come from the real numbers, and since we're talking about addition there, it all really does follow from the same way. However, what we're going to talk about next is with multiplication. And when we talk about matrix multiplication, things get a lot more complicated, and the results from the real numbers do not always follow. So we're going to talk about matrix multiplication in a couple different ways. We've already done this in an earlier section, but we're going to be a little more careful now with what we're doing. So if I take a matrix B and I multiply it by a vector x, we think about that as transforming x into the vector b. This is from our linear transformation section in chapter 1. But if you take bx, that takes a vector and turns it into a new vector, bx. So it's like we have x, and if we multiply that by b, we get a new vector, bx. Then, if we multiply a by bx, we transform bx into a times bx. So then this is going to be a composition of those two matching. It's like we have another thing here where that is multiplying by a, and I get a times bx. And we're going to show that this is the same thing as a times b times x, and that's how we're going to think about it first, how to find the matrix multiplication AB. So we're going to do a little abstract math here, right here. That's going to be find AB by looking at this multiplying by a vector x. The vector x is really not that important in this example, but we'll see that in a second. So let's suppose that A is an m by n matrix and B is an n by p matrix. It is very important that these two entries, the n and the n here, these must match if you want to do matrix multiplication. The inside entries have to match, and we'll see why that's the case later on. So B is an n by p matrix, so we have these n vectors and p of them. And then x is just an arbitrary vector of length p that could be any real numbers there. So if I take b times x, that is a linear combination of the columns of b with the entries of x. We have x1, b1 plus x2, b2 all the way to xp, bp. And if I take that thing and multiply it by a on both sides, so I have a times bx on the left and then a times that linear combination, from the results that we said before about the properties of real numbers attributing to matrices, I can distribute that a to each of these sums and get a times x1, b1 plus a times x2, b2 all the way to a times xp, bp. And then, since we have scalars, x1, x2, all the way to xp, those are just numbers, we can bring those out in front of vectors or of matrices. So I could write this as x1 times, should be xp, x1 times all of these vectors. And that would be another way to write a times b1 plus a times b2, all the way to a times bp. These are vectors times the vector x. So, if we go all the way back, we know that a times bx is the same thing as this matrix times x. And if I get rid of the x's, I am left with the definition of AB, which is AB is going to be written as these columns, AB1 times, or AB1 in the first column, AB2 in the second, and then ABP in the pth column. And we also showed that a times bx is equal to abx. We could multiply the matrices first and then multiply by x, or we can do multiply by x first and then by a. So let's see a specific example of this going on. So we're going to compute AB, where A is given by this 3 by 2 matrix, 3 rows, 2 columns. And we're going to multiply that by this 2 by 2 matrix, B. Note that if this is going to work, we need these 2's to match up. They do, so this is all going to be fine. So we said that the definition of AB, just write that over here real quick, is going to be A times the first column of B, and then A times the second column of B. So that's what we do here. We have AB1 is going to be the matrix A as a whole times that first column of B, 2, 6. And to do that, we know we can do a linear combination of the columns of A. This is going to be 4, 3, 0, that column A times 2, plus 6 times -2, -5, 1. And if I do 2 times 4, see what I'm doing here, 2 times 4 plus 6 times -2 is 8 minus 12. I get -4. We can continue doing that to get the other two numbers. And that gives me the first column of AB, that -4, -24, 6. Similarly, I can do AB2, but this time looking at the second column, -3, -7. Writing that out, that will give me -3 times the first column of A, which is going to be 4, 3, 0, and then -7 times -2, -5, 1. And I just noticed that this matrix is not the right matrix here. That's matrix B. This should be the matrix A, 4, 3, 0, -2, -5, 1. This should now match up with our linear combination that we're talking about here. And again, we get a new matrix, 2, 26, -7, a new vector. That comes from the linear combination here. -3 times 4 is -12. -7 minus 2 is +14. If you add those together, you get 2. We can do that for the other two entries as well. And we get this new vector, 2, 26, -7. And that defines our product, A times B. So our product of A times B is coming from our definition of the product of matrix vector multiplication. And note that AB1, the first column of AB, is a linear combination of the columns of A, and AB2 is a linear combination of the columns of A. So we can say that each column of AB is a linear combination of the columns of A using weights from the corresponding columns of B. So here we go. We have a new example. Let's look at a 4 by 3 matrix and a 3 by 2 matrix. And let's think about what are the sizes of AB and BA. So here, note that A times B, we have 3 and 3 here. These must match in order to do the matrix multiplication. So I don't care what the entries are here. I'm just going to try to figure out what is going to be the size of my matrix AB. And to do this, let's look at an example, specific example, just to see for one of these entries what's going on. So let's say we have a 4 by 3 matrix, 1, 2, 3, 4, and then I don't really care what the rest of the entries are, times, let's just do 1, 2, 3, 4, 5, 6. So if I'm talking about the first column of AB, that's going to be A times B1. That's going to be this entire matrix. 1, 2, 3, 4 times 1, 3, 5. Then I am going to take the first entry of B, 1, times the first column of A, plus the second entry in B, times the second column of A, plus the third entry in B, times the third column. And that'll give me the first column of AB1. And then I can do that again, but this time with the second column, the 2, 4, 6, and that would give me this second row, which means that I would have a 4 by 2 matrix. And the way that I like to think about it is if we have a 4 by 3 matrix and a 3 by 2 matrix multiplying together, these entries have to match, and they match and they kind of get ignored, and the result is a 4 by 2. Let's look at the opposite multiplication there, b times a. So this is a 3 by 2 and a 4 by 3. And in this case, because the 2 and the 4 are not the same, this is undefined. This doesn't make any sense to do. And we could think about this again, why this is the case. Let's see what would happen if I take these entries together. So let's look at our example. Let's do 1, 2, 3, 4, 5, 6 times, let's just do 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2. So using our definition, we have that the first column of BA1 will be B times the first vector in A, and that would give us 1, 3, 5, 2, 4, 6 times 1, 2, 3, 4. But this multiplication doesn't make any sense because this should be the linear combination of the columns of A. So this should be 1 times 1, 3, 5 plus 2 times 2, 4, 6, the second column of that matrix B, plus 3 times, there's nothing there, and then plus 4 times, there's nothing there because we've already used the columns of B. This doesn't make any sense. This is undefined. These entries have to match. So our result here is if A is m by n and B is n by p, we can multiply those matrices together, A times B, and our result is m by p. And another quick thing that we got from here is that if we have AB and BA, AB is not the same thing as BA. In this case, we can't even think about what is BA in this example. This is not the same as real numbers. This is definitely true for real numbers, but it's not true for matrix multiplication. So we're going to look at a different way of computing AB. This is what we're going to use usually because the definition is good for theoretical work, but when we have small sizes of matrices, it's good to just do a much quicker row by column method of computing AB. So here, AB is defined, and we're going to let AB sub ij, that is the entry in the ith row and the jth column of AB. And we can define that by looking at the ith row of A and the bth column, or sorry, the jth column of B. And we're going to multiply those in a dot product like fashion to get ABIJ. So we take the first entries of that row in the column and add them together, or multiply them together, and we're going to add the second entries. We're going to go all the way down to the last entries and add them together to get that specific entry. That's one entry of AB, and we have to do that for all entries to find our matrix. So let's do an example. We're going to let A be this 2 by 3 matrix. We're going to let B be this 3 by 2 matrix, and we're going to compute AB. Note that 3 and 3 are the same there, so we can multiply these, and the result should be a 2 by 2 matrix. So what we're going to do is, if I want to find the AB11, the entry in the first row in the first column, I'm going to look at the first row of A and the first column of B and multiply those together to get this entry. So that is 2 times 2 plus 3 times 0 plus 6 times 4. 2 times 2 is 4, 3 times 0 is 0, 6 times 4 is 24. Add those together, and we get 28. Then I have to do that 3 more times to get the other 3 entries of AB. So the second one will be 2 times negative 3 plus 3 times 1 plus 6 times negative 7 is negative 45. That is the first row, second column. Sorry, first row of A, second column of B is the entry in the first row, second column of AB. Second row of A, first column of B gives me that next entry. 1 times negative 2, 0 times 0, 1 times 4 will give us a positive 2. And then finally, second row, second column gives me the last entry, negative 1 times 4, 0 times 1, 1 times negative 7 gives me a negative 4. And that gives me my matrix AB. In this example, I want to show what the definition is, just to show that we're really doing a lot of the same work, just in a different order. So looking at the definition, AB, we have that this should be AB1, AB2. So looking at that first entry, that's going to be the matrix 2, negative 1, 3, 0, 6, 1 times the first column of B, 2, 0, 4. I'm only going to do the first column there. And then this is going to be a linear combination of the columns. That's going to be 2 times 2, negative 1. Plus 0 times 3, 0, plus 4 times 6, 1. And I just want to bring your attention to the first multiplication here. That is 2 times 2 plus 0 times 3 plus 4 times 6. And note that that's the exact same first multiplication that I did when I did this row by column thing. We had 2 times 2 plus 3 times 0 plus 4 times 6. And then note that the second one we have, 2 times negative 1 plus 0 times 0 plus 4 times 1, corresponds to this part of the multiplication. And the other 2 entries have that same corresponding feature. We can do this matrix multiplication either way, but we are going to do in practice this row by column. It's a lot quicker when we're dealing with small matrices, and we're only going to be dealing with small matrices by hand. So let's talk about some stuff that we can do with multiplication. All of these still kind of follow from the real numbers, but there are some things that we cannot get. So again, we're going to let A be n by m, m by n, and B and C have sizes for which the indicated sums and products are defined. In order to add matrices together, they have to be the exact same size. And the matrix multiplication we talked about, what has to be true. Those inside entries have to be the same. So we do have the associative law. It doesn't matter what order that I multiply those matrices in. I can distribute from the left or from the right. We don't have a differentiation between left and right multiplication in real numbers because it doesn't matter, but in matrix multiplication land we do. And we can multiply by a scalar in any order, so we can multiply by A or B first. And then an important one that we're going to use a lot is the identity matrix. Just gives us a matrix back, and I can multiply by the right or the left to do that. The big thing here is this warning that although this is very similar to properties of real numbers, not all real number properties correspond to matrix properties. The first one we've already seen, that A times B does not equal B times A. In fact, it's usually not even defined. We'll look at an example in a second that when it is defined, it doesn't even work though. This is called the cancellation law, part 2. If AB equals AC, then B may not equal C. In the real numbers, this is definitely true. If you have 6 times 3, and this is equal to X times 3, then we can say that 6 is equal to X, because we can just cancel out those 3's. We cannot do that in matrix multiplication land, and we can look at this example right here. Here I have 1, 1, 1, 1, and negative 2, 0, negative 2, 0. If I multiply those together, let's do that real quick. I can take the first row, first column, it's going to be 1 times negative 2. And I really do want this, to be a positive 2 there to make this work in a different way, even though it would still work out. 1 times negative 2 plus 1 times 2 is 0. 1 times negative 2 plus 1 times 2 is 0, and the other two entries are going to be 0 because we're multiplying by the 0 column. And if I do the same thing again, if I should have a positive 3 here, I should get the exact same thing out. So these two matrices are the same product, but it's clear that we're using different matrices to get there. This is also an example of part 3. That you can have two matrices multiplied to give you 0, the 0 matrix, but they don't have to have 0 matrices to do that. That is a huge property of the real numbers that's used all the time, that you can't have any two real numbers multiplied to give you 0 unless one of them is 0. Note that if you take either of these multiplications we did in the example and you flip them, you will get a different matrix out, showing that AB does not equal BA in general. In fact, it's very difficult to find an example. I wouldn't say difficult, but it's very uncommon to have an example where that does work out. So then a couple different things. We're going to look at the powers of A and then the transpose of A. So the powers of A, if you take A to the K, that is taking the matrix A and multiplying by itself K times. So let's look at an example. We have the matrix 1, 3, 0, 2. This is a 2 by 2 matrix. And if you multiply that by a 2 by 2 matrix, the entries will be the same, and you're left with just a 2 by 2 matrix. When you're multiplying matrices of the same size, you will always get a matrix of the same size back. So A to the K will always be the same size as A. To do this, we can multiply A by itself first. So let's do that. That'll be 1 times 1 plus 0 times 3 is 1. 1 times 0 plus 0 times 2 is 0. 3 times 2 plus times 1 times 3, it's 3 times 1 plus 2 times 3 is 9. And then 3, 2, and 0, 2. 3 times 0 plus 2 times 2 is 4. And if I take those two matrices and multiply them together, then I get this matrix 1, 0, 21, and 8. And note that this is not equal to just taking the entries of A and cubing them. It's close. We have the 1, 0, and 8 match up, but this 21 is not the same as 3 cubed. So it's not that easy. You do have to go through the multiplication step by step. There's some nice formulas for some matrices, but in general, you have to kind of go through that. Another thing we're going to look at a lot is the transpose of A. So if A is m by n, the transpose is you're going to switch the rows and the columns. We're going to have n by m. And then again, that is where the columns are formed using the corresponding rows of A. The columns become the rows become the columns. This is denoted by A to the capital T, A transpose. So here we have, there should be 3, 1, 2, 3, 4, 5 becomes the column 1, 2, 3, 4, 5. The row becomes the column. The row here 6, 7, 8, 9, 8 becomes the column 6, 7, 8, 9, 8. And the row 7, 6, 5, 4, 3 becomes the column 7, 6, 5, 4, 3. Rows and columns are switched. So let's let A be this 2 by 3 matrix, B be this 3 by 2 matrix. Because those entries 3 and 3 match up, we can compute AB, and we're going to look at a couple different things here. So if I do A times B, again, we're taking the first row, first column. 1 times 1 plus 2 times 0 plus 0 times negative 2 is 1. If I take the first row and the second column, that is 1 times 2 plus 2 times 1 plus 0 times 4 is 4. Second row, first column is 3 times 1 plus 0 times 0 plus 1 times negative 2 is 1. And second row, second column, 3 times 2 is 6, plus 0 times 1 is still 6, plus 1 times 4 is 10. So that's A times B. If I want to find A, B, and then transpose it, the rows become the column and the columns become the rows. So the first row is 1, 4. That'll become the first column, 1, 4. The second row is 1, 10. That becomes the second column, 1, 10. Now let's look at a couple other things. We're going to look at something A transpose B transpose. There's a reason that we're doing this. So A transpose is the rows become the columns, B transpose, rows become the columns. And if we do this out, we get a 3 by 2 matrix and a 2 by 3 matrix. The 2's match up, and we're left with a 3 by 3 matrix. You can go through that multiplication if you want. One that's even more important is this B transpose A transpose, just reversing the order that we're doing it. And here we have 1, 0, 2, 1, 2, 0 is going to give us a 1. 1, 0, 2, and 3, 0, 1 will give us a 1. 2, 1, 4, and 1, 2, 0 will give us a 4. And 2, 1, 4 times 3, 0, 1 will give us a 10. And it is not a coincidence that these are equal. In fact, in general, A, B transpose will be equal to B transpose A transpose. And let's look at that on the next slide. So some properties of products with the transposes. If we have A transpose transpose, that's just A. If you switch the rows and the columns, and then you switch the rows and the columns again, you just get back to A. They kind of cancel each other out. Stuff with adding with matrices is pretty simple. So A plus B transpose is just A transpose plus B transpose. That works out the way that you want it. Same with scalar multiplication. If you multiply a matrix A times R, and then transpose it, that's the same as taking the transpose, then multiplying by R. The difficulty is when you talk about matrix multiplication, and in this case, AB transpose is not A transpose B transpose, but the reverse of that. So the last thing we'll do here is we're going to look at this result, ABC transpose. We're going to try to figure out what this is going to be. And we're going to use this last theorem to do it. So ABC transpose, we could look at this kind of piece by piece. So let's look at first AB times C. If we do that, then by part D, that is two matrices multiplied together and then take the transpose. So we're going to do the opposite order. That should be C transpose times AB transpose. But then note that AB transpose we know is equal to B transpose A transpose. So then our final result here is C transpose B transpose A transpose. And that's what we wanted to get here. We're going to work with this transpose a lot in the future, as well as with the powers of A. And obviously we're going to be multiplying matrices and adding matrices together a whole bunch. This is a setup for the rest of the course. that we can do a lot of things that are similar to real numbers, but not everything with matrices.